So this is my video on 16.8, which is Stokes theorem. So you may recall that earlier when we did Green's theorem. So what does the Green theorem do? So what the Green theorem does, it's actually when you have a two-dimensional region, and if you look at the boundary curve of that region, the Green theorem actually connects the line integral along the boundary curve with the double integral, with a certain double integral of the region. So basically, without you can get information about what's happening inside the curve. That means in the region by integrating along the curve. So by getting information from what is happening along the curve, you can get information about what is happening inside the curve. So in this section, we are doing kind of like, and that's the Green theorem. In this section, we have Stokes theorem is kind of like the 3D version of that. So what we are going to do is instead of a two-dimensional region, we are going to look at a three-dimensional surface, right? And that surface must have an oriented smooth surface that is bounded by a simple closed smooth boundary curve. See, and I will put up a different, maybe a video explaining what that means, but for the time being, with positive orientation. So we just imagine a surface, right, which has a boundary curve, which is closed and smooth, right? And suppose we have a vector field F, and we are trying to see whether we can get information about the flux of that vector field. Well, really the flux of the curl of that vector field using a line integral on the boundary curve. And that's what it essentially does. It says that the line integral of the vector field along the boundary curve C is equal to the flux of the curl of the vector field through the surface S. So again, we have a surface S, which has a boundary curve C, right? And we have a vector field F. What it does is actually connects the line integral like we did on Green theorem, but now in 3D with, instead of the double integral of the region, we are now taking the surface integral of curl F, or in other words, the flux of curl F across the surface. So the flux of curl F across the surface is equal to the line integral along the boundary curve of the surface. That's what it is. Now to see whether this is correct, let me try a simple illustration. So what we're going to do is we're going to take this, let S, our surface, be the upper hemisphere or the upper top part of a unit sphere. Okay, so we have unit sphere, right, means a sphere with the radius 1, and look at the upper part of that. And let's call that surface our S. And let C be the boundary circle. So basically, C will be the circle that this unit sphere's upper hemisphere traces on the XY plane. Okay, so we have the surface, we have the curve, and suppose this is our vector field. So now let us see whether this is correct, this formula. So first of all, we'll take this part of the formula. Let's see. So let's calculate the line integral. And then we will show that that is equal to the double integral or the area integral of the curve. Okay. So let's find the line integral. So it's 2x, then it will become 2x dx plus x dy plus y dc. So we know that, and then let's now try to see whether we go to our boundary curve, which is the unit circle on the xy plane, and then it is very easy to parameterize that. And we can just parameterize it using x equals cosine theta and y equals sine theta, the polar coordinates, right? We can parameterize the circle like that, okay? And then of course this is on the circle is on the xy plane, so there is no c, so c is equal to 0. Alright, so if you plug in that, then we know that if c is equal to 0, this part is 0, right? And because z is equal to 0, dz is also 0, this is also 0, so we are left with this. So the line integral is really x dy. Now, what is x? X is equal to cosine theta. Now, if you convert the dy into the thetas, y is equal to sine theta, so dy will be equal to cosine theta d theta. Okay, and then what we do is we have cosine theta, which is cosine squared theta. Now the theta range is the how theta moves on the xy plane. Okay, so that will be 0 to 2 pi. So this is even power of the cosine, and you know how to integrate that. That's using the double angle formula. So we will write it as 1/2 1 plus. From calc 2, you may remember this. 1 plus cosine 2 theta. Okay, so we can take the 1/2 outside. So the integral of 1 is theta. Integral of cosine 2 theta is sine 2 theta over 2. And we take the limits at 0 to 2 pi. So if you plug that in, you will notice that when you plug the 2 pi to the sine or 0 to the sine, it becomes 0. So you are only left with 2 pi minus 0, which is 2 pi, and 2 pi times 1/2 is just pi. So the answer is pi. So the value of the line integrals across the boundary curve, okay, which is the unit circle, okay, and of this hemisphere is equal to pi. So in this formula, we now know that the left-hand side is equal to 5 pi. Now let's check out the right-hand side. So the right-hand side is the curl, the flux of the curl. So we need to find the curl. So if you find the curl, it's pretty easy because the curl you can find, and you can show that the curl of this one by taking the cross product with the divergence operator, right? Okay, and I won't go through that. So if you take this as your vector field, you can show that the curl of this is 1 to 1. So now all we need to do is to take the surface integral of 1 to 1, right, over this hemisphere. Okay, and by definition, we saw in our video about the flux or the surface integral of a vector field. The surface integral is nothing but so this is our vector field curl of f, right? Yeah, and times r phi, the partial with respect to phi and partial with respect to theta. Well, why do we do that? Because we're dealing with a sphere, it's natural for us to parameterize the sphere using spherical coordinates. So when you use spherical coordinates, you will find that r phi cross r theta is equal to this. So we now take the dot product of the curl with that, right? And we have d phi d theta, and then we have this, right? And so sine squared phi is come, and we have sine squared phi, and we take the dot product. So we have sine squared phi cosine theta plus 2 sine squared phi sine theta, and then and we have that, and we do the integral, right? And then and we can finally show that this integral is simplifies and equals pi. So after we convert this into theta and phi, it's a straightforward integral that we need to do, and the integral is pi. And which is the answer? So this side is also pi, this side is also pi, so pi equals pi, which means that the result is true. So what we did was not actually a problem, but we actually gave an example to show that to illustrate Stokes' theorem. So now let's look at an example. So it says use Stokes' theorem to evaluate the curl of the flux of curl f, where the function is given like this. So, and the surface is given as this surface above the plane z equals 1. Okay, so the boundary curve therefore will be phi minus x squared minus 1, right? Because we are talking about the plane is equals 1, which will give you x squared plus y squared equals 4, which is a cylinder, but it is on top of the cylinder, it is crossed by the planes equals 1. We can parameterize this now using cylindrical coordinates. So is x equals 2 cosine theta, y equals 2 sine theta, and z equals 1. So then once again, by using Stokes theorem, right, this is equal to the line integral across the curve, the surface curve, and so we take a function which is this, right, and we do that, right, and then so now we are going to do is we are going to we know that this the flux of the curl is equal to the line integral of f across the boundary curve, right? And we know that the boundary curve is given by x squared plus y squared equals 4 and s equals 1, the circle, right? Okay. And so f we know is given by z squared minus 3xy and x squared. So it will be z squared dx minus 3xy dy and x cube dz.
So now what we are going to do is now we are going to parameterize this curve. So we have c squared dx minus 3xy dy plus x cubed dx integral. So x is equal to 2 cosine theta. So dx is equal to 2 sine theta. And so that's what comes here, right? Okay, and negative, right? Okay, and then we have 3xy dy, so x is 2 cosine theta, so 2 cosine theta comes here, and then y is 2 sine theta, so 2 sine theta, and y is 2 sine theta, so dy is again 2 cosine theta, so another cosine theta comes here, so there are 2, 2, 2, and there's a 3 outside. And then if you go to this last part, right, okay, because z is just 1, it's a constant, so dc is 0, so this is 0. So in the end, we come to negative 2 times sine theta 0 to 2 pi, and this becomes 3 times 2, 6, 12, negative 24 cosine squared theta sine theta d theta, right? Cosine squared theta sine theta d theta. Now, if you put a u substitution here, put u equals cosine theta. This you can show that is actually u cube, right? Okay, and which will really give you in the end this cosine cube theta, and you can see that when you take the derivative of cosine cube theta, you're going to get 3 cosine squared theta sine theta, so you get the cosine squared theta sine theta term. So but when you put this up here, right, okay, so this part sine theta 0 to 2 pi is 0, and cosine cube theta, so 2 to 2 pi is also 0, so the final answer is 0, which actually means that the uh, the flux of the curve through this surface is actually 0. There's no flux through the surface in this case. Thank you very much for watching.